Hello, my name is Alice. Welcome to our collection of training modules covering the many software programs we offer to customers seeking a comprehensive design for their separator. This video is for VSEP-Calc Plus. There are many design options for vertical drums, such as the examples you see here, each of which is engineered to meet specific performance requirements under different operating conditions. VSEP-Calc speeds up the separator design through the use of various drop-down selection options, and by instantly showing you the effect of changing design parameters. Let's take a look at the program in more detail. When you open VSEP-Calc, you will see two tabs, an Instructions tab, and an Input-Output tab. Let's take a quick look at these. The Input-Output tab is where the vessel design is done, and we'll come back to this shortly. The Instructions tab, as with all our programs, lists the program version and the license details. Here you will also find the general recommendations for selecting the design cases, and which variables have the most impact on the sizing and performance. For this program there is also guidance for nozzle sizing, liquid holdup and alarm settings, and style of mist eliminator. The sizing K-factors for the mist eliminator can be adjusted here in the Instructions tab, should you wish to deviate from the default industry standard figures. At the bottom of the page, you will also find a brief history of the program revisions. Now, looking at the Input-Output tab, at the top we find the standard document control boxes where you fill in the details of the issuer, revision description and date. Note the main box here should have your company name in it. You can edit this if required. Complete the project and vessel details here. And select the units, metric or FPS, that you will be using. There is a choice of designing to 2 or 3 phase, gas, liquid or gas, oil, water, by using this macro button. The 2-phase option gives a single printout page. The 3-phase option uses a 2-page printout and requires additional layout choices. We'll come to that shortly. You have 2 design cases for your data entry, and you need to fill in all the flow and physical property details. Note that if you have 0 oil or water flow for one of the cases, you should specify 0 in the flow rate box. But don't put 0 in the fluids property boxes as that upsets the calculations. Just use typical figures, or those for the other liquid phase that you are considering. Next you should select appropriate nozzle sizes to give you acceptable velocities and momentum. Simply edit the table here with the nozzle ID to instantly see the data for the 2 cases. Now you can select an appropriate inlet device to suit your inlet momentum in accordance with standard industry guidelines. The selection of vessel diameter is based on 2 factors, gas flow and liquid flow. Usually, one of these dictates the size. And you can use the program to quickly see if the vessel is gas or liquid constrained by checking the liquid residence time and the gas K-factor. First, specify a simple vertical flow mesh pad demister to get a feel for the recommended diameter. We can optimize this later if it's too generous. Take the mist eliminator diameter, add a margin, and enter it as the selected vessel diameter as your first estimate. Next, adjust the liquid levels to give a suitable residence time in accordance with typical industry standards. Depending on the fluid and the application, minimum holdup at normal liquid level is generally between 1 and 5 minutes, with 1 minute, or 4 inches, minimum between alarms. If the levels appear too tall, it is liquid constrained and so increase the vessel diameter. If the holdup is too long, consider reducing the vessel diameter and using higher gas capacity internals, such as vanes or cyclones. Try a few modifications of the internals choice and layout to obtain the optimum vessel size for the duty. Your 2-phase model is now almost complete. Simply confirm the selected tan-to-tan vessel height and save your design. Before we move on, let's take a look in more detail at the gas space within the vessel. The calculations use a simplified form of mist eliminator design to give a suggested demister diameter or size. Note that a more rigorous design, together with predicted droplet removal performance, is available using our separate SEP-Calc program. When you specify the vessel diameter here, you will see that the gas K factor changes here. You should check this to ensure it is in line with typical recommendations for the style of separator that you have chosen. These K factors can vary quite a lot, so keep that in mind. To help in your considerations, the program also calculates the maximum rising droplet diameter that is lifted up by the vertical gas flow, in accordance with established settling laws. This also gives the designer a feel for the liquid loading hitting the demister. Larger droplets mean a higher liquid load. Below this is the maximum falling droplet diameter that is theoretically achieved by the coalescing of lots of droplets together before it breaks up under drag forces. However, sometimes, due say to very low surface tension, the maximum droplet size can be smaller than expected. We therefore highlight the likely droplet diameter in a green box here, from the two calculation methods. Now let's take a look at three-phase operation. After pressing the three-phase option button, and filling in all the data as before, except we can ignore the liquid levels on page 1, we head to page 2 where we set out our preferred layout. From the sketch at the bottom of the page, we see a typical layout for three-phase operation, where the inlet liquids flow along a sloping partition plate and fall into a downcomer. From here the liquids are dispersed into the bulk phase where they separate into two layers. We can select the type of downcomer, the liquid levels, the weir height and the oil sump dimensions on this page, whilst checking as before, that residence times are appropriate. At the bottom here, we also calculate the liquid-liquid separation performance in case an additional coalescer pack is required to meet the target specification. Let's fill in an example. This vessel is 900 mm diameter, and so we need a compact arrangement. We'll select a pipe downcomer, with plain end, not perforated, and try a couple of diameters to reach an acceptable, low velocity. The oil bucket width can be reduced a little to allow more residence time in the bulk space, thus achieving better performance. With a spillover weir, the oil bucket levels are set here to give reasonable residence times and performance. You can also have a submerged weir if there is no risk from water overflow. By adjusting the various dimensions and levels, you can get a feel for how the performance changes with aspects of the design, leading to a valid optimization.